This lesson is about Newton's laws of motion. This is the first lesson in the dynamics unit. Dynamics is the branch of mechanics that's concerned with forces and their effect on motion. Let's start by talking about Isaac Newton himself. He was an English physicist and mathematician. He was born in December of 1642 and lived until March of 1726. He was educated at Cambridge University, and he was known for quite a few things. He developed the mathematical field of calculus. He was the president of the Royal Society of London, which is an elite organization of British scientists. And he was appointed the Master of the Royal Mint of England. What's important to us is that, among other things, he studied gravitation and its effect on the orbit of planets. In 1687, he published in Latin a book titled Philosophia Naturalis Principia Mathematica, which translates to The Mathematical Principles of Natural Philosophy. This is often just referred to as the Principia. It is widely regarded as one of the most important works in the history of science. Upon his death, Newton was buried at Westminster Abbey in London. Let's take care of some definitions. First of all, mass. This is a scalar quantity, and it is a fundamental measure of the amount of matter in an object. Next, we'll talk about force. This is a vector quantity, which means it has direction, and this can be described as an interaction that may result in the change of motion of an object. In other words, it's a push or a pull. There are three laws of motion as defined by Isaac Newton. We will refer to them as inertia, F equals ma, and action-reaction. Let's start by taking a look at Newton's first law. Newton writes, "Every body perseveres in its state of rest or of uniform motion in a right line, unless it is compelled to change that state by forces impressed thereon." You might not really get what that means, but it makes a lot of sense. Newton is saying that an object sitting at rest on your desk is not going to start moving for no reason. Something would have to push it or pull it, right? Something would have to exert a force on it. Likewise, without something like friction or air resistance or other objects to collide with, a moving object keeps moving at a constant speed indefinitely. In this video, we are looking at a crash test of a car. And you can see even though the car stops, the dummy keeps moving, right? It keeps moving at least until forces are exerted upon it, right? Forces are exerted upon its chest by the steering wheel and its head by the windshield. It's very important to understand the relationship between inertia and mass. The more mass an object has, the more resistant it is to a change in its motion. This means it has more inertia. Inertia is a property of an object that resists a change in motion. More mass is more inertia. Here's a video I took of me flicking a paper cup. On the left, the cup is empty. On the right, the cup is full of quarters. Each time I flicked them with basically the same amount of force. The cup on the right, which is much more massive than the cup on the left, resists a change in its motion a lot more. Right? The cup on the right has more inertia than the cup on the left. The cup on the left, being so light, is very easy to change its state of motion, or in this case, its state of rest. Okay, let's move on to Newton's second law. Newton writes, "The alteration of motion is ever proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed." Let's take a look at this first section first. Newton is telling us that acceleration, which is what he's describing as the alteration of motion, is directly proportional to the force. He also tells us that acceleration is inversely proportional to the mass. If we put these two relationships together, we get an equation for Newton's second law. A equals F net over m. We'll talk about what that net means a little bit later. This is commonly written as F net equals ma, and that's why we refer to this law as F equals ma. On your reference table, this equation is in the form A equals F net over m. Okay, let's take a look at this second part. It says that the alteration of motion is made in the direction of the right line in which that force is impressed. This is just a fancy way of saying that the acceleration of an object is always in the direction of the force that is causing it. The acceleration is always in the direction of the force that is causing it. Let's take a look at the units that we get from this equation. So we have the equation F equals ma. M is mass, and it is measured in units of kilograms. A, of course, is acceleration, and it's measured in units of meters per second squared. F is force. If we multiply kilograms times meters per second squared, nothing really combines or cancels out. We end up with kilogram meters per second squared. This is defined as a newton. Right? The unit for all forces is newtons. Let's take a look at an example of a problem involving Newton's second law. A 30-kilogram child on a swing is pushed by an adult with a force of 120 newtons. What is the acceleration of the child while the adult pushes? We'll answer this problem like we do any other problem. We'll write down the equation that we're going to use. We can substitute in the information that we know, 120 newtons over 30 kilograms. We would find that the child's acceleration is 4 meters per second squared. Now let's take a look at Newton's third law, action-reaction. Newton writes, "To every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts." What we care about is this second part. What Newton is saying is that when two objects interact, they each experience a force. These forces have the same magnitude and they have opposite direction. Here's a video of kind of a kooky physics professor on a skateboard with a fire extinguisher. When he pushes down the handle to expel gas out of the fire extinguisher, the gas is pushed sort of toward us, right? In turn, the gas kind of pushes the fire extinguisher and, of course, the professor holding it away from us.
4, 3, 2, 1.
This is a really great example of action-reaction as described by Newton in his third law of motion. All right, let's summarize this lesson. The first law states that objects persist in their state of motion or rest unless they are acted upon by an unbalanced force. We also know that inertia is directly proportional to mass. Newton's second law tells us that the acceleration of an object is directly proportional to the force exerted upon it and inversely proportional to the mass of the object. This can be seen in the equation A equals F net divided by m. And Newton's third law tells us that when two objects interact, they experience forces that are equal in magnitude and opposite in direction.